jointly. Our next talk will be David Campbell from Clemson on statistical perspectives on the human factor in spot data from RBN and WSPR networks.
Sorry, I was muted. Can everybody hear me and see the big screen?
Yep, looks good. Take it away.
So I'm David Campbell. I'm an undergraduate student at Clemson studying math and economics, but don't worry, there's not going to be any money talk. We're focusing more on the math side. I've been working with Dr. Deborah Kunkel on the statistical perspectives on the human factor of RBN and WSPR networks. Like was just mentioned, the contests are a big human factor in all the science that you guys have been talking about. And so let's get first started with the data we're using. We included data from both the RBN and the WSPR networks. I think this data on this slide is from the RBN network, and this is sort of the raw data from the spots that we got from the F5IN call sign. So these spots include time, date, call sign receiving, call sign transmitting, the locations of each, in Maidenhead coordinates, the frequency and the band. And the first thing we needed to do was clean the data. So, and when I say clean, it really just means make it into something that we need so that we can use it. So this data is for a different call sign, the VE6JY. And I have the locations of both of those in a little later in the slides. And so now we have date and time sort of split up, latitude, longitude, and now we have the number from the call sign on the date, the total from the transmitting location, the total on the date, and the total on the date from the transmitting location, all going to this one call sign. So that will allow us to look at the statistical model a little later. We also rescaled all of these counts. So each one of these are counts, and we wanted to rescale all of those just to make it, because counts can get really high and really low, rescaling it makes it a little easier to look at and analyze, so that we don't have one data point skewing the data completely. But first, we created an app to look at visualizations of this data. So we looked at the F5IN call sign. That's in, it's in Dadonville, France. And first we have this histogram. First, I'll go through what we can do with this. So we can break it down by year. So if we just wanted to look at 2019, we can uncheck all those boxes. And now we're just looking at data from 2019 on the 40-meter band, and we're looking at the entire day. We can also change the hour of the day. So I guess hour 1 is midnight to 1 a.m. And on this specific chart, we see that this sort of becomes a zoom feature. So now we can look at from midnight to 10 a.m., or we can look at all day. It's important to note that that midnight to 10 a.m., I don't think we made this UTC time, so we have to deal with time zones. So this might actually be the middle of the day, which I think it is, because that's where most activity is. And this would probably be nighttime. And we can add maybe the 15-meter band, and we see that the counts change a little bit. Now we can look at a date frequency chart. We'll add in all the years again. And if we see, so again, when we take out the 15-meter band, it changes a little bit. And so we see these big spikes. This one especially so this chart has every single day from January 1st, 2016 to December 31st, 2019. And so it looks like sometime around February in 2016, there was a lot of activity. And then we could even make this number, if we could make it 3, it would break it down, or make it 4, we could break it down by year. If we make it 41, it subsets into 41. But if we make it 1460, it does every day. And we can look at, again, hours 1 to 10 sort of shows us that much. most of the activity. And if we make it sort of hours 12 to midnight to 24, we lose a lot of that activity. So now this is a time series of each year. So each different color is each year. Again, in 2016, on day 30 of 2016, so that tells us exactly when it was, January 30th, 2016, F5IN received 3,359 calls on the 40-meter band throughout the entire day. We can also change, again, we can change any of these, but these spikes are really what interested us in wanting to develop this model to sort of eliminate the human factor in the science that you guys have been talking about all day. And we also can see these on a map. It takes a second to load. So because this one's in France, we can see a lot of spots coming from Europe. So this call sign EA5WU was very active. The more yellow, the more active, the more blue, the less active. So UR5FCM was only one spot, so it's a darker purple. And I will copy and paste this link into the chat in case any of you want to. Actually, Dr. Kunkel, I know Dr. Kunkel's in the chat. Can you copy and paste that into the chat so people can look at it? I'm having trouble finding the chat. Perfect. Thank you. All right. So now that we have that those visualizations gone through, and you guys will have this app to play around with on your own if you would like to, we'll start talking about the statistical model. The motivation for this, I talked a little bit about with the app. We see a lot of the spikes in the count. So we wanted to sort of eliminate the human element or just acknowledge the human element. And so our goal was to estimate a function that predicts the number of spots heard from a fixed location on a particular date. And to do this, we wanted to use a Poisson generalized linear model. And why this model counts that we have a similar distribution to the Poisson distribution. So it starts high, sort of at 0. It starts high and comes down and tails off is what the Poisson distribution looks like. And generally in statistics, when we have counts, we want to use a Poisson distribution. So this Poisson generalized linear model, or GLM, is what we wanted to use. Our response variable, so the variable we're trying to predict, was that count of spots to a call sign on a date. Same sort of thing as I mentioned in the goal. To do this, we're going to use the count of spots on a date, counts of spot from each location, count of spots on each location on each date, so that's kind of an intersection, and then distance. So for distance, we use what's called a spline. This just allows this variable to find a flexible function to model the effective distance, and that just allows for it to be a better model. And so this is the scary math screen, or the first of, but hopefully I can explain them well enough. If we see, so the model is the log of lambda of t of s and s is equal to a coefficient times x1 plus a coefficient times x2 plus a coefficient times x3 plus a coefficient times x3 squared plus a coefficient times the function of distance. So this lambda t comma s is a function of counts of spots that a call sign receives on a given date t and a location s. And for x1 sub t, that the t is just another helpful notation thing to remind you that it's the number of spots on the date t. And then x2 comma s is the number of spots from location s. And then x3 comma t comma s is that sort of that intersection, the number of spots on that date t from that location s. And the g of d of s is a smooth function of distance from receiver to transmitter. And that is what we use the spline to create. And the data we used for this model specifically was data from the WSPR network for December 2017 only. And so again, I put the final model up there because I know it's a lot of math to remember. And for this, for the first time we made this model, ran this model through in R, which is a statistical software, we used the DK8FT call sign, which is in that part of Germany that there's no way I'm going to be able to pronounce. So this is a lot of numbers. So the first column is the coefficient. So beta 1 is this number 0.06. And I'll interpret that one a little bit. So that beta 1 is the log, when the log of the expected counts increases by 0.06, when the rescaled value of x1 increases by 1, or another way, expected count is multiplied by e to the 0.06 when the rescaled value of x1 increases by 1. So that's a mouthful and kind of hard to interpret practically because of the log scale that we're using. So what we really like to look at here is just the magnitude and the sign, positive or negative, of each of these variables. So we see that the date is an okay size positive. The location is actually negative, but it's fairly small effect. And then we see that this location squared term is negative, but that really just balances out the effect of the x3 value, date and location value, that is positive and a very large magnitude compared to the other ones. And this x1 to x15 is a result of the spline that we used for distance. So you can kind of group these all together as the distance variable. And we see that they're all negative and about the same size as the date and location. So we see that the effective distance is negative, which makes sense because the further away, maybe the less likely to call. And in statistics, we like to look at residuals to make sure that our model is doing well. The main thing we look for here is that there's no pattern in these residuals. So unfortunately, you actually see kind of a pattern in this one. And I do apologize, I accidentally included Maidenhead coordinates instead of the DK8FT, I think it was, for the call sign in these titles. But you do see kind of a squiggly line pattern in this first residual plot, which we added the x3 squared term to try to eliminate, and it worked a little bit, but there's still a little bit of that there. So in the future, we're going to try to eliminate that. And fortunately, you don't see too much of a pattern with these other three spots. And then the next thing we wanted to do was try to see if this works for another call sign. So we went to VE6JY in Lamont, Alberta, Canada, and we see very similar results. So we see that the date is 0.09, the coefficient on date is 0.09, but we do see that the coefficient on location becomes positive and about the same magnitude as the date. So that's a change, but not shocking. I think it's a little more shocking that it was negative in the last time we ran it. This x3 squared term stays negative, and the date and location x3 term stays fairly large comparatively and stays positive, along with distance staying negative for the most part, which is great because that tells us that we can sort of plug in the data from other call signs and get some very similar results, which is the goal. Again, we look at the residual plots, and we see this little tail at the end of this little squiggly residual plot for the date and location, this first residual plot, which we hope to eliminate in future work. And lastly, we like to look at the residual histograms. So if we look at what we want to look for here is that these histograms look similar, and they do, which is great. So that tells us that the model worked very similarly for these two different call signs, and hopefully in the future we can just have it run on a bunch of different ones and they all look very similar. And so that is our ultimate goal, and we're on our way there. And conclusions, kind of walked through most of the conclusions throughout that, but our future work, we hope to expand the model to include frequencies, time, and other variables. predictive checks, and using other Bayesian methods. Bayesian methods are just another part of statistics that could help us. And we're very open to working with members of the community and really want that. So if you have any questions or want to work with us, please reach out. My email is on there. Dr. Kunkel's email is on there. She might be easier to reach than me over email, but please reach out if you want to help, if you have extra questions. And I think we do have a few time for questions. Dr. Kunkel is also in the chat to answer questions. I think she has been doing that. Thank you.
All right, thanks very much. Dr. Kunkel, feel free to turn your mic on and join us in the panel discussion as well. We have 5 minutes before we go to break, but first a couple of questions on this. I think I'll start with Gary's. He asks, scary math question, how did you arrive at the final model formula?
Oh, I'm still unmuted. Okay, great. So the final model formula is actually not as scary as it looks or not as scary as it sounds. That formula is just basic regression that you'd learn in like an intro statistics class. So it's really just the same for every statistical model out there. You just kind of throw in like a log here if you want it, or just keep adding variables. The x3 squared term, so the location and distance term squared, is the only part that's really complicated that we got to. And that's, we looked at those residual, these residual plots and saw that it was sort of polynomial shaped, so sort of like an x3 or an x cubed or an x squared graph. And so we added that term to just see if it balanced out a little bit more. And so it's not as scary as it looks to get to because of it's just kind of there in statistics. I'm sorry if that's not a great answer.
No, I think you're good. There's a good discussion going in the chat, and I'm not going to try to recapitulate the whole thing, but there's some discussion of the skip zone being evident in the data, which is worth noting. Phil asks, have you thought of looking at the full distribution as well with respect to, e.g., distance?
I'm going to be honest, Phil. I'm not really sure what you mean.
All I mean is, this is Phil. All I mean is that, you know, you can reduce some of these variables, but, you know, keeping around the full distribution of what you have there and not necessarily parameterizing it, it's like there are patterns in there that we don't know about because we don't know to look for them, right? And you have a model, but that might not be the only model that would, for example, pick some of those up. So looking at the residuals as you're doing, after you put the model in, you might discover extra pieces of information that we don't know about, that we wouldn't expect, for example, from our conventional physics understanding of what's going on. So those residual plots like you have on the screen, I seriously encourage you to retain those and do some analysis on the residuals themselves.
Yeah, yes, absolutely. I think that's the next step. We've been working on, we developed the app for a while, and we just recently got to this model.
Yeah,
so we've done a little bit of residual analysis, but I think that's the next thing we really want to dive into.
I think as statisticians, you would look at the flavor of those residuals in maybe a different way than, for example, the physics person might. And I think that viewpoint might discover some new things in here.
Yes, absolutely. That's the goal.
All right. Well, we're very excited, I think, to see this this analysis because spot data is something that there's been a lot of work on in our corner, and the human factors part of it particularly, to see that reviewed in a rigorous way is really excellent. So we are coming up on the break. I think this discussion may continue on its own, but I'm going to officially hand over the conch to, let's see, Carl and Veronica. You are now the moderators. Oh, and Bill. Didn't mean to skip you there. And
that's fine.
Yeah. All right.